All right, let's get started. Thanks everyone for taking the time to be here today. My name is Neha Deodhar and I'm a software engineering manager in Google. I work on the Cloud Spanner team. Today I'm going to be talking about how you can scale your businesses using multi-region configurations in Cloud Spanner. I hope this is going to be an interactive session, so do feel free to ask questions as I'm presenting. So here's the agenda for today. I'll go over some brief introduction for Cloud Spanner and give you an overview of the architecture. We'll then dive into how regional and multi-region configurations work in Cloud Spanner. So you get an idea of what sort of use cases are useful for regional, what sort of use cases would you use multi-region configurations for. I'll also go over the different replica and read types that are available. And then discuss how Cloud Spanner handles failure. So let's say that you have a server, zone, or region failure. How does Cloud Spanner handle it and continue to ensure that the database remains available for you? So what is Cloud Spanner? In a gist, it's a distributed relational SQL database that supports ACID transactions. It brings the best of both SQL and NoSQL worlds. Like SQL databases, it supports relational schema structure, ACID transactions. It is strongly consistent. It supports the highest consistency guarantee, in fact, called as external consistency. It supports ANSI SQL. At the same time, like NoSQL databases, it is highly scalable. It has 5 nines of availability. It's a fully managed database service, so you don't need to worry about doing any cluster administration or database administration, doing failovers, none of that. All of that, this is taken care of for you by Cloud Spanner. A lot of mission critical applications and services within Google use Spanner, so it's been battle tested in that sense by Google. Now here's how Cloud Spanner works internally. Now, when the data within your database is divided into chunks, what we call as splits. So in the above example here, consider that you have 2 tables, singers and venues. The data across those 2 tables might be split into different chunks. So in this case, in this example here, it's split into 4 different splits. These splits are then balanced across different servers to ensure that you can get good throughput for your data. The splits are also, note that these splits are not static, they're dynamic. So if your load to your database increases, so let's say that split 3 suddenly starts getting more data, we will split that further, or Cloud Spanner will split that further into 2 separate splits. We also do split merging. So if there are 2 splits, you delete a lot of data, and then the 2 splits that can be merged, it might merge them into 1 split. Now, along with splitting your data and balancing it across different servers, Cloud Spanner also replicates your data across different failure domains. So in case of regional configurations, it'll replicate your data across different zones. It can also replicate your data across different geographical regions. Now, in order to replicate and synchronize the data across your different zones, we use a consensus algorithm called as Paxos. So if you see here in this example, you have n splits for your data. All of those splits are replicated across 3 zones. Now, you have 3 copies for each split of your data. Now, each split has 1 copy or 1 replica, which is designated as the leader. Now, this leader election is done using the Paxos consensus algorithm. The leader replica is then responsible for doing the writes. And in order to ensure strong consistency of your data, it will ensure that at least 2 out of 3 replicas, or a majority of the quorum, or it uses a majority quorum in order to commit the write. Now for transactions that involve multiple rows, so let's say that you are doing a write that goes to multiple splits, your write will now need an extra layer of coordination, or your write transaction will need an extra layer of coordination called as a 2-phase commit, where the different splits act as participants in the 2-phase commit, and then there's 1 split which acts as the coordinator and coordinates the transaction. Also note that because these servers are distributed, Cloud Spanner uses something known as true time to ensure that the data across the geographically distributed servers is consistent. So TrueTime is a highly available distributed clock that is on all Google servers. It lets you generate monotonically increasing timestamps, and it can guarantee that the generated timestamps follow a correct external ordering. So what this means is that using TrueTime and Paxos consensus, we are able to give you external consistency, which means that the writes, as your application does the writes, it's the same ordering as what you see in the database. Your database will follow the exact ordering that you do in your applications, even though the writes may be happening on different geographically distributed servers. Now here's a brief diagram of how writes in Cloud Spanner works. So it's a simplified version of how a write in Cloud Spanner will work with a single split. Now your client, when it issues the write first goes to the leader replica. The leader replica will then replicate that write across the two other replicas, and then wait for a vote from those two replicas. Note that a vote is essentially an acknowledgement of the write. Now note that we require a majority quorum to mark the write as committed. So in this case, the majority quorum will be two replicas, the leader replica itself, and either one of replica 2 or replica 3. So the leader replica will wait for either replica 2 or replica 3, and depending on who responds first, it will consider the write as committed and respond back to the client. Any questions so far? All right. Now, Cloud Spanner configurations, instance configurations, there are two types that we support. One is a regional instance configuration, and the other is a multi-region configuration. Now, in a regional configuration, we have your data is stored in a single geographical region. So, for example, it could be stored in Iowa or it could be stored in Oklahoma, but like one geographical region. Within that, we replicate your data across 3 zones. The reason we do that is to ensure that if some servers go down or even a zone goes down, you continue to have your data being available. So in this case, you see that your splits are replicated across 3 zones. Now, even if zone 1 was to go down, you will still continue to have 2 copies of your data available in zone 2 and zone 3. And that way, your database can continue functioning and you can still function even in case of a zone failure. Such configurations give you a 99.99% availability, so 4 nines of availability. Typically, applications that are in a single region, or if your application has some regional data governance requirements, then regional instance configurations are a good choice for you. So imagine that you have an application, where your data needs to reside in Germany for legal reasons, and you can't have your data reside in any other region. For such configurations, regional instance configuration might be, for such applications, regional instance configuration will be a good choice. These also give you good low latency reads and writes within the region because your application happens within the same single region. The other type of configuration that we support is a multi-region configuration. Now, this is suitable for global applications that might be spread across multiple geographical regions. Now, there are various aspects to multi-region configuration. So I'll go over some of these today. Now, at the very least, multi-region configurations, we want to ensure that you are able to recover from zone as well as region failures. So even if one full region goes down, your application should continue operating. In order to do that, we create 5 copies of your data, and they are replicated across 3 zones. So if you look at this example here, so this is an example NAM Europe Asia configuration that we have. Here you have 5 copies of your data. 2 copies are stored in Iowa, 2 copies are stored in Oklahoma, and 1 copy, which we call as a witness copy. I'll get to that. I'll get to what a witness copy is in a little bit. But we have a 5th copy stored in South Carolina. Now with 5 replicas, you need a quorum majority of 3 out of 5 in order to commit the write. So this means that even if one region goes down, so let's say Iowa goes down and these 2 replicas are no longer available, you still have 3 replicas in Oklahoma and South Carolina available, and your application can continue operating. So even when the whole of Iowa fails, your application remains unimpacted. One of the reasons So one thing that I want to call out here is that for Cloud Spanner, our writes always do synchronous replication, which means that let's say that you have a leader in Iowa. When it replicates the write to the rest of the replicas, it's a synchronous write to all the other four replicas. And you wait for an acknowledgement from two out of the other four replicas to come back before committing the write. Now, in order to do this, you want to make sure that the replicas that are involved in your writes are close together, because you don't want to wait for a very long time for an acknowledgement from a faraway replica. So this is why you'll notice that the write quorum is entirely based in the US, because we want to make sure that your write latencies continue to remain low. Now, if you have a global application that's spread across the world, so let's say you have some users in Asia, some users in Europe, in order to serve faster reads for those users, you can use what is known as read-only replicas in those regions. So in this configuration, for example, we have additional read-only replicas, 2 in Taiwan and 2 in Belgium. And those can serve low latency reads to the users in Europe and Asia. Such configurations give you 5 nines of availability, and they help you recover from a higher number of failures. So zone as well as region failure is what they can tolerate. Now, drilling into the details of the read, write, and witness replicas a little more. Like I mentioned before, Cloud Spanner replication is synchronous, and because you want to wait for an acknowledgement from majority of the replicas involved in the write quorum, you want to ensure that these regions, the 3 regions that you select as your read-write regions, are relatively close to each other. So at least in the same continent, or let's say within 1,000 miles of each other, or so on. These read-write replicas, they all store a full copy of your data. So reads can be served by any of these replicas. So you don't have to serve the reads. It's not like only the leader serves the reads. Any replica can serve the read. Writes are only done by the leader replica. So depending on where your splits leader replica is, that leader replica will be responsible for coordinating the write. Notice that the third region is what is known as a witness region. Now, the reason we have this witness replica is that it makes it very easy for a Cloud Spanner to achieve a full quorum or a write quorum without requiring a full copy of your data. So the witness region, the witness replica in South Carolina will store a full transaction log of the transactions that are happening in the system, but it won't store a full copy of your data. So you cannot use it to serve your reads. You can only use it to vote for your writes. Now, read-only replicas are a way for you to scale your reads to additional regions. So, if you have your write quorum in this example in North America, and you have users in Asia and Europe, and you want to serve low latency reads to those users, then the read-only replicas that are based in Asia and Europe come in handy. So these replicas, they store a full copy of your data and can serve reads. Note that they don't participate in voting for writes. So this ensures that you're not waiting for a replica in Asia, or you're not waiting for a replica in Europe to vote on your write, and your writes continue to remain unimpacted and have fairly low latencies. Now let's look at how reads work in Cloud Spanner. Like I mentioned before, reads can be served by any replica. One interesting aspect is that Cloud Spanners by default will always try to read the latest data. So such type of read is called as a strong read, where you want to make sure that you're always reading the latest data that has been written to the database. Such reads may require communication with the leader to make sure that the replica that has received the read request has the latest data. Now, to explain what this means, imagine that you have this database which is spread across 3 zones. Now, a user requests for data or requests for a row that's in split 2. The request will go to a replica in zone A. Now, this replica may not be the leader replica. So it will try to look up its internal metadata to see if it has the latest data or not. If it is unsure of whether it has the latest data, or if it knows that it does not have the latest data, it will then contact the leader to get that information and then respond back to the client. So because strong reads may require communication with the leader, replica, they can add a delay to your reads. This becomes more apparent in multi-region configurations where, let's say, you have a read-only replica in Europe and you're trying to do a strong read there. If the replica is not sure whether it has the latest data or not, it might have to communicate with the leader based in North America, adding some cross-region delay to your read. Now, to avoid that, we have a concept of stale reads. Now, this is useful for applications that can tolerate slightly stale data. And by stale data, I mean few seconds stale. So I'm okay with reading, let's say, 10 seconds or 15 seconds stale data that's 15 seconds old or 10 seconds old. But my application wants much lower latencies. So I want to avoid that cross-region communication with the leader. Such applications can benefit from using stale reads. So in this case, the user will make a request for a read and it will say that, hey, I'm looking for a read with max 15 seconds staleness. And now the replica that receives the read may not require communication with the leader and can serve back a read very quickly. The other concept that I want to go over is something known as a default leader region, which again exists in multi-region configurations. So the data in Cloud Spanner is divided into splits. And as we saw before, each split has its own leader. So consider this NAM Europe Asia example. We have replicas and we have splits spread across 3 regions. So there's a split, the splits are spread across Iowa, Oklahoma, and South Carolina. Now, if I have a split whose leader is in Iowa, and imagine that I have a split whose leader is in Iowa, and I have a split whose leader is in Oklahoma. Now, if I have my application that's based in Oklahoma, and I'm reading data from the split that's based in Oklahoma, I'll end up getting very low latency for my, I'll end up getting a very low latency for my write. Now, if I have a row that I'm writing that's based in a split whose leader is in Iowa, then my write will see a high latency. So what ends up happening is that we see unpredictable latencies if the split leaders are spread across different regions, because now depending on which region your application runs in and which region the split leader might be in, you'll see different latencies. So to avoid that and to provide a more predictable latency performance, Cloud Spanner has this concept of a default leader region, where we'll try to ensure that the split leaders are placed in the default leader region whenever possible. We also recommend that application instances align with the default leader region for better write latencies. So this ensures that the writes from the application always start off with the leader region and see a better latency profile. One of the things that I wanted to clarify is this concept of node versus replica. So we've seen some user confusion around the concept of node and a concept of replica in Cloud Spanner. Now, replica is a copy of your data. So in single region configurations, you will have 3 replicas of your data, irrespective of the number of nodes that you have in your instance. And in a multi-region configuration, you will have 5 or more copies of your data, 5 or more replicas. Node is the amount of compute and serving resources that are available for your instance. So when you set up a Cloud Spanner instance, you can specify the number of nodes that you want for your instance. And this number of nodes only specifies how much compute power you're going to get. So if you have a 1 node replica versus a 1000 node replica, your 1000 node replica has a lot more compute power than your 1 node replica. So if you see here in this example, this is a 1 node instance. It has 3 replicas and there is some amount of compute or serving resources that are available to you in each zone. If you have a 2 node instance, it still has 3 replicas or 3 copies of your data, but now you'll have 2x the amount of compute resources in each zone. All right, any questions so far? Okay, so let's move on to how failures are handled in Cloud Spanner. Now, starting with a multi-region configuration. We have an example configuration here where you have region 1, which is the default leader region, region 2, which has 2 read-write copies, and region 3, which is witness. Now, under normal situation, let's say like a normal situation when all replicas are up and running, your majority quorum might be these 2 replicas in region 1, and let's say the replicas in zone A of region 2. Now, if your leader region goes down, then Cloud Spanner will try to move the leader to another replica. So in this case, it's possible that leader 2, the replicas in leader 2 might become, the replicas in region 2 might become the leader replicas. And the majority quorum ends up being the 2 zones in leader 2 in region 2 and the 1 zone in region 3. So this way, your application can continue operating without any downtime, even when the leader region and spanner fails. Note that Cloud Spanner clients can automatically retry failed requests. So let's say that your client has an outstanding request when region 1 goes down. So that particular request will be retried by the Cloud Spanner client. So when region 2 becomes the leader, the client will retry and the request will get satisfied with region 2 as the leader. So because it does this retries transparently to your application will see an intermittent increase in latency, but it won't see any downtime. So your request won't fail, or it'll just see an increase in latency as Cloud Spanner client is doing the retries. Note that when the leader region comes back up, the leaders will again move back to region 1, because that's your preferred leader region, and Cloud Spanner will try to honor that whenever possible. And again, this leader movement is transparent to applications, so for all practical purposes, nothing should be visible, or there should not be any impact to the applications as to where the leaders are. Now let's consider what happens when some other region fails, right? It's not the leader region, it's some other region that ends up failing. Now in this case, imagine that, under normal situations, region 2 and region 3 form the quorum, majority quorum, and region 2 is the leader. When the third region, the region 1 goes down, nothing changes from the point of view of the majority quorum. It still remains region 2, region 3. There's no impact on application for writes, and any reads that were being served by region 1 will now get redirected and will be served from the next closest available region. So maybe from region 2. Now let's look at what happens in case of a zone failure. Now this is a more interesting case if the zone failure is in the leader region. So let's imagine, again, go back to the example where your majority quorum consists of 2 zones from the leader and 1 zone from the second read-write region. Now in this case, when zone A fails, all the leaders that were in zone A will now move to zone B. So note that Cloud Spanner will try to ensure that the leader continues to remain in the same zone. So we won't, as long as it's available. So we won't move to zone A in region 2. Instead, the leaders will move to zone B in region 1 and continue to maintain the default leader region. The quorum will now change to maybe zone B from region 1 and then all of region 2. So as before, there's no downtime on applications. Applications might see an increase in write latency as clients retry some intermittently failed requests. Similarly, for a regional instance, zone failures are handled in the same manner. You have a majority quorum which consists of 2 zones out of 3. If one of those zones that are in the quorum fails, the majority quorum now shifts to the other 2 zones. So as long as 2 zones are available, the regional instance will continue to be available. All right, so that's all I had on multi-region configurations. Please do feel free to try out Cloud Spanner locally. We have something known as a Cloud Spanner emulator, which lets you use Cloud Spanner for free or try out Cloud Spanner for free on your local laptop. I have provided a link to a quick start guide. We also have a good developer ecosystem with a lot of tools and client libraries in different languages for Cloud Spanner. So do check out Cloud Spanner ecosystem on GitHub. And for more information, there are a number of blogs available on Google Cloud Spanner page. With that, I can open it up for questions if anyone has any questions. No questions? Either I was super clear or super confusing. All right. I think we can wrap it up if there are no questions. Thanks, Vijay. I think we can wrap it up if there are no questions. Thanks, everyone, for your time. Do feel free to check out our blogs.